We're good.
Yes. Welcome to another lecture of 2DM3, Discrete Mathematics, Calculational Mathematics and Applications. As usual, I have a bit of music as per requested. If you don't like it, please let me know and I'll turn it off. Or if it becomes bothersome, I will turn it off. Just let me know. So you should be able to see my screen. Please let me know. Sometimes I'm afraid I'm just talking to myself in a room. And, I'd like to make sure you guys are there. So occasionally just be like, yeah, algebraic, mathematical, and other things you say in daily life. So let's just turn off the music now. I feel I'm getting in the way. Yeah. So just yesterday we talked about the theorem true, and I just updated the abridged / supplemental lecture notes to indicate the benefits of this theorem. And I added some little tooltips that might help, or not. So we shall see. Okay, ducks. I would like to actually do live calc check in front of you, live coding. So hopefully we can do that. If you guys don't want me to do that, please let me know. If you're like, no, just explain things, don't type stuff up, please let me know. Okay, ducks. Alrighty then. So you will have seen, or you will see, in one of the homeworks, there's going to be a reverse presentation of command correctness. So I'll show you that in a moment. We're going to wrap up with disjunction and conjunction today, chapter 3, 3.3 and 3.4, I think. And then we'll get to inductive definitions of natural numbers, induction proofs. So the first part is really easy. The middle part is kind of easy as well. The last part kind of depends on knowing what an inference rule is. So hopefully nothing too difficult. Please ask questions. Some things might be harder than they seem. Okay, ducks. So if you remember when we talked about program correctness, one of the things we said was always start working at the bottom. Start working at the bottom and work your way up. All right. So we said start here, then apply the assignment rule, and we want you to go upwards. All right. So even though you're starting at the bottom, you go up to get down here. Now that seems a bit contrived. Why would you start the bottom? Why would you when you read a piece of text, you start at the top and work the way down. That's how English is usually read. Why are we asking you to do it this way? So we asked you to do it this way just because if you start at the bottom, program correctness pushes what you want, your goal. It pushes your goal through the program until you have a precondition, right? So our goal here on the left-hand side is x equals 12, and we want to perform an assignment. And so our goal is x equals 12. We want to perform an assignment, and the assignment rule tells us, hey, push x equals 12 through this substitution, and then we simplify, and then we push it through another assignment because we're doing a sequencing, and then we work all the way up, all the way to x equals 5. We're simplifying. We start at the very bottom, we simplify, and along the way we perform some assignments. Okay. If instead you read it from the top, from x equals 5 downwards, you'll realize the very first thing we're doing is adding 1 for no reason. Why would you do that? That's why would you add 1 to both sides? What's the motivation there? What in the world are you doing to add? Like, there's no reason to do this. Why would you start at x equals 5 and say, you know what? I'm an oracle. I know the future. I must add 1 to both sides. Why would you do that? All right. So this approach, we showed it to you, so we don't have to introduce multiple operators at the beginning. We don't want to confuse everybody. But that was the only time where we did it, just as an introduction material. The way people normally do it is working backwards. Notice on this side, we actually do start from the top and work to the bottom. We start at x equals 12, and we actually right away we say x equals 12 follows from, right? Remember this backwards implication is follows from. So x equals 12. This is a result of your program. This is what's going to happen. This is a consequence or a result of performing this assignment, which requires that you replace x with y plus y everywhere. So we're doing substitution here, right? Notice we're fusing 2 steps instead of 1, all right? So here we have 2 steps, all right? And over here we split it up in, each step was performed in 1 line, okay? So we'll talk about how many hints you can perform in a step, but ideally not so many that CalcCheck gets stuck or that it's hard for another human reader to read it, okay? So for now, we've only been doing 1 hint, but we'll slowly show you that you can do more than 1 hint in the steps. And the book talks about this as well, okay? But notice everything is natural. We start at x equals 12, and we say we want to perform this assignment. So the assignment rule says x equals 12 is a consequence of the assignment, provided we have y plus y equals 12. Okay, we want y plus y equals 12. So notice right here, we're just simplifying. We're just saying, hey, I want to factor it out. So y plus y is 2 times y, right? That's the whole point of what we're doing here. And then I'm dividing both sides by 2. So that's what this process is doing. So I think in the homework, I have you do this as a theorem that says y plus y equals 2 times y, all right? But for now, we're just showing you this because it was shown over here. So that way it doesn't look so contrived, okay? So we divide, and now the next step is, this is a consequence of performing an assignment, right? And then we do that, and then we simplify. Notice, we have x plus 1 equals 6, and now we're canceling, we're getting rid of extra information. We had x plus 1 equals 5 plus 1, and we simplified to x equals 5. So when you do it this way, you have a particular goal in mind. Simplify, right? Start with the most complicated thing, or with the end goal, and simplify to get back to the precondition, okay? So hopefully you'll be comfortable to use this reverse operation. Just as I mentioned yesterday, implication is like less than or equal to on the numbers. So follows from, or reverse implication, is like greater than or equal to on the numbers. If you're interested in the details of this comparison, I've added a few paragraphs on the supplemental lecture notes, and you can see why implication and this program correctness implication are really, really, really close to less than or equal to. And the reason we have to keep track of the programs here, whereas for less than or equal to, we don't have to keep track of a witness, is because the witness is unique for numbers, and for programs, it's not. There are many programs that can take you from true to true, for example, right? So interesting stuff. Hopefully you'll keep that in mind. Okay, dokes. So this is, I think, the 3rd lecture or 4th lecture where we've talked about equivalence. So I'm not going to spend too much time on it. Just equivalence is, I wanted to spend some time on it. All right. So equivalence is symmetric, like addition and equivalence. It's associative, mutually associative, and you can interchange it. So as we've said numerous times. So hopefully you can prove these. For the upcoming midterm, you should definitely be able to prove these kinds of results. Okay, dokes. We talked about this unfold-fold strategy. Again, this is chapter 3, all right? So if you see right here, 3.23, and the book has a number of heuristics to help you make your proofs, okay? When you encounter something that's new, you call on its definition, you work with stuff you're familiar with, then you call on the definition, and you pack it up, okay? So the unfold-fold strategy is just, this is a new thing, I don't know what properties it has, let me get rid of it. Now I have familiar stuff using the definition, I know properties about those, let me manipulate it. Now I got what I want, and let me pack it up using the definition. Okay, dokes. Please stop me if you have any questions, concerns, or queries. Okay, dokes. So this is a theorem we saw the other day. There's not much to be said, just we unfolded right here. We know equivalence is symmetric, so we applied that, and then we folded. Okay. So this is a very useful technique, and it'll come up every time we define a new operator. In a few slides, for example, we will define a new operator. Okay. So just as yesterday when I talked about truth tables, and I said, you know what, you can understand an operation by how it evaluates, right? How it simplifies, right? For example, or. If the first argument is true, the whole thing is true. If the first argument is false, then I have to look at the second argument. This is a particular implementation of the operation or. Okay. But what we can do is say, you know what, rather than always evaluating, for example, if I ask you, what can you tell me about P or P? You can't tell me anything about P or P. You have to either know P is true or P is false. Right? You don't know anything about P or P. But if I give you some axioms, some properties that pin down the operation, that define it uniquely, then you don't need to evaluate anymore. So for instance, P or P is just P. Right? So for instance, I tell my friend, hey, you can have apple pie or you can have apple pie. There's the illusion of free choice. You will have to have apple pie, right? P or P, right? Or if I say, what's the maximum of 5 and 5? Well, the larger of 5 and 5 is just 5. There is no choice to be made. So maximum is also an idempotent operation. Incidentally, maximum is also symmetric, associative, idempotent, okay, but it does not satisfy these two rules over here, okay? So or is like maximum and is like minimum. And again, the comparison, I've left it to the supplemental lecture notes. Put a nice little chart there for you. Okay. Distributivity of or over equivalence. This is like multiplication distributing over addition, right? So I can take P and I can throw it inside, and then I'll have P or Q equivales P or R if I read it this way. If I decide to read it the other way, then I have a factoring rule, okay? And finally, excluded middle. Excluded middle is everything is or isn't. There's no middle ground. There's no gray, all right? Either you know it or you don't. Real life doesn't work like that, but formal mathematics does. So a very important thing to remember. In real life, it's not, you know, you pass or you fail. There's a gray area, all right? It's not you know it or you don't. There's a gray area. You're in the process of learning. You're in the process of knowing, right? So please remember these formal logic doesn't always apply directly to life. Bertrand Russell, and I hope some of you are excited, and if you don't know who that is, that's okay. Bertrand Russell and his friend Alfred North Whitehead proved this amazing result. The amazing result is 1 + 1 = 2. They proved that result in Principia Mathematica, and I think they did it after 372 pages of setup to make sure their logic is set up. So hopefully you'll be able to prove 1 + 1 = 2 later today, or at least next week. The last law that I mentioned a moment ago, the law of the excluded middle, is everything must be or not be, right? There are logics that don't have the law of the excluded middle. For example, probability theory, you can consider 1 to be true, 0 to be false, and then any number between 0 and 1, that's a level of truth or a degree of truth. So probability theory is a kind of logic that does not have the law of excluded middle, okay? Many logics do have the law of non-contradiction. Nothing can both be and not be. So for example, probability theory again, right? When people talk about probability theory as if it was a logic, they sometimes call it fuzzy logic because it's true or false or it's fuzzy somewhere in there. I don't know, right? And since we showed that true is a theorem, and by equanimity or equivalence, if something is equal to a theorem, then that thing is also a theorem. So because true is a theorem and this thing is a theorem, we will usually use it in this shape. Whenever we have P or not P, we'll usually say, oh, that's equal to true. We can collapse that into just true. So some of you saw this on the midterm where you saw things like even to. And you're like, what does even to mean? And that was mean of us. We didn't mean to trick you. Even to means even to equals true. Okay. So hopefully whenever you see a theorem T, you know that means T equals true. Okay, docs? Are there any questions, concerns, or queries? No? All right. Can somebody just confirm they actually hear me and I haven't gotten muted or anything? Please?
We can hear you.
We hear you.
All right, I got 4 friends. Great. So just as we talked before, you're playing a game. All right. Here are the rules of the game. So these five rules define the operation OR. So before I told you, you can think of OR as being here. Let me type it up. So this is a particular implementation of OR. All right. P or Q equals, and we'll get to this. You'll be able to prove this later on. If P is true, then true, else Q. Okay, so you can. This is a particular implementation. All right. If P is true, then just true. We're done. Otherwise, return Q. Okay. So this is called short circuit evaluation. This implementation just looks at P. So for example, if Q said x divided by 0 equals 23, x divided by 0 is not defined. So that's a very weird thing to ask. But nothing will crash in your program, because if you say true or x divided by 0 equals 23, well, this definition of OR just looks at the first argument, and that one is true, and so we stop. We don't even look at the second argument. Okay. So this is a particular implementation. Sometimes this is called short circuit disjunction, short circuit or conditional or, conditional C, or conditional or core. Right? But we will avoid it, right? So we'll use this cyan or cyan box up here to delimit the definition of OR. Now, since that's the starting point of the game, now you have a bunch of rules you can prove, right? So you had to prove on previous homeworks and assignments that zero laws and identity laws. So here's more practice to prove them. So the very first homework had you to prove an identity law. So here's one. Try to prove it. Okay. The book shows you how to prove this law right here. So using that for insight, you can try to prove this one and the ones that come after it. The book explains how to do the proof for zero of OR in detail, and it tells you what heuristics to follow. In particular, the left-hand side is complicated, so you start with the left-hand side and simplify till you get to the right-hand side. Okay, dokes. So let's move on, and please always interrupt me if you have questions. I'm happy to stop and talk. This this is exactly what I was saying. I had forgotten it was already here. Okay, so we want to get to true. So we start off with the complicated side, P or true, and we simplify to get to true. Doing this other way is not ideal. You have true, and for some reason you say, oh, let me make it more complicated. But why? Why would you do this? This is like at the very beginning. There's no motivation. Why are you introducing P or P? Why not introduce 2 plus 2 equals 2 plus 2? Why this one? So there's no motivation for these kind of steps. And so life will be very hard. You're just kind of shooting in the dark, hoping things work. So we will always try to do this kind of idea. All right, start with the complicated stuff and simplify. Right, we want to avoid these surprising things like why has this happened? Why? So a lot of math books, unfortunately, will do stuff like this. They'll say, oh, true is the same as P or P equals P or P. So we can factor out that P, and then we have P or P, and that's just true, and so we're done. And those books, maybe those authors just want to feel smart or clever, but they're not very good books to learn from. So that's unfortunate, to learn how to do proofs from. Okay. Since equivalence is associative, we're defining a new operation. So again, this is where that fold-unfold strategy comes from. So here's P and Q, and we're going to say P and Q is defined to be equal to this thing. Okay. Some of you might think this is very complicated, but because equivalence is associative, you can read it as this way, right? You can say, hey, and is this particular operation such that two things are equal precisely when their and is equal to their or. Okay. I'm just curious, does anybody think this is a really weird definition or not? Everyone thinks this is a normal
It's
definition.
kind of weird.
Or is everything in this class weird, and so this is
It's
just
weird.
All right.
It's weird.
It's weird. All right, great. That's really what I wanted. I wanted you to all tell me that it was weird, because that's what I wanted to hear. What if I wrote it like this, though? What if I said x equals y equals x, x, did I caps lock? X minimum y equals x maximum y. How do you feel about this? Who feels this is weird?
It's weird.
It's still
Wait,
weird.
no. So if I have two numbers and I say, hey, these numbers are the same precisely when the minimum of them is equal to the maximum of them. Doesn't that make sense? Like, if I have two numbers and I say, hey, here's their maximum and here's their minimum. Oh wait, the max and the min are the same, so the two numbers must be the same. Does that sound more reasonable?
Yes.
All right.
Yeah.
What if I wrote it this way then? What if I said x min y is equal to x precisely when y is equal to x max y? Okay. So I'm saying the minimum of two numbers is the first one precisely when the other one is the maximum. Does that sound reasonable?
Yeah.
Yeah.
Okay. So for the real numbers, this is such an obvious thing and so uninteresting that no one tells you that, hey, if you have two numbers and you take the minimum of them, all right, you take the minimum of two numbers, then the other one has to be the maximum, right? It just sounds so obvious that no one wants to write it down. But when you get to propositional calculus, this fact is so useful that it can define what minimum means. So remember, the Booleans are ordered by implication. So and is like the minimum operation, and or is like the maximum. Okay. So minimum, the order doesn't matter, right? Minimum is associative. The minimum of 2 and 2 is just 2. Okay. If the minimum of a number and positive infinity, if you like to think of it as positive infinity, is always the first number. The minimum of, I'm sorry? Was there a question? And the minimum of a number and negative infinity, if you like to think of it that way, is always going to be negative infinity. All right. So true is all the way up in the heavens, positive infinity, and false is all the way in the depths of the earth, negative infinity. And you can think of and as a minimum. Okay. And then you'll be able to be like, yes, these are obvious things about, numbers if I order them from top to bottom. And is self-distributive, distributes over itself, just like minimum and or and maximum. And a thing P cannot both be true and not true. Okay, so this one, we can't talk about this one in the numbers. This one's special. So the minimum doesn't have this particular property. This is only for the Booleans. Because if you have a thing that's P and it's true, then its opposite is going to have to be false. And the minimum of a true thing and a false thing is false. Okay, so that's all that says. Yeah. So let me know if you have any questions, concerns, or queries. Let's prove a theorem. Do I have time to do it in person? Let's maybe do it here, and then if we have time, I can maybe open up a notebook and we can do some of them live. Okay, I'm just keeping an eye on the chat in case somebody has something. Okay, so just as I mentioned before with the idea of fold and unfold, the very first thing we say, hey, I don't know what this P and Q thing is. It's new, but I'm familiar with equivalence and I'm familiar with or. So let me call on the definition. I call on the definition, and I know that equivalence, you can swap things around, right? So I swap things around, and I know that or you can swap things around. So I do that too. Okay, ducks. So swap here, swap there, and use the whole thing as the definition of and. Then I know, wait, this is just the definition of and again, and I'm done. All right, so that's the idea. Get rid of new strange stuff, work with familiar things, do the work there, and then go back to the new strange stuff. Okay, ducks? All right. And then we can prove a number of properties. And again, you can interpret these, if you like, in terms of numbers, right? The minimum of a number, along with the maximum of something else, including that number, is just going to be the number, all right? So you can think of them as number properties, if you like. The ones that involve and, not as easily. So these ones, you can also think of these as number properties involving maximum and minimum, okay? De Morgan is very special. De Morgan says if you have P and Q and having both of them is not true, it is not the case that both are true, then what does it mean that a bunch of things are not true? It means that at least one of those things is not true, okay? So when I say it is not the case that everyone has ice cream, what I'm saying is at least one person has ice cream, right? So Mary doesn't have ice cream and Bobbert. It is not the case that Mary has ice cream and Bobbert has ice cream. Means Bobbert doesn't have ice cream or Mary doesn't have ice cream. Okay, and likewise for or. Sorry. Yeah. If you don't want to ask verbal questions, feel free to message me in the chat, and I will see your questions there. Okay. So again, as I've been saying repeatedly, and maybe I'm getting to be a broken record, but just if you practice, you'll know which theorems to use. So sometimes when I show you things, it looks like it seems maybe out of grasp and out of reach, but with enough practice, you'll get an idea of how to do these things. And the book is filled with these heuristics that tell you how to what to do and to guide you in making your proofs. Okay, and we're going to try to keep giving you homework after every lecture to help with that as well. Okay. So we're going to move on to the natural numbers. So I just want to know if anyone has, I'd like to pause and see if anyone's interested in seeing a proof done in CalcCheck for equivalence or and or are you all comfortable with that and we should move on? You can send me a private message if you want me to look at it, but you don't want anyone else to know. Okay, so we'll move on. Or am I mute?
Or I think one proof would be nice. Samples are always good.
What is it? Hello? Okay, so somebody wants to do a proof somewhere. All right, let's do that.
Can you do a proof with a golden rule?
I can, but will I? Yes, I will. It's completely fine. So let's go to one of your notebooks, and I think we have De Morgan maybe is on one of them. Let's find out. So here's assignment 1. Assignment 1 contains all of midterm 1 and conjunction. Okay, so let's do some stuff from the conjunction notebook. Is the screen big enough? Do you want me to make it bigger? Oop, is this better? Is this better? Oop.
Yeah, that's better.
It's good.
Right. So here's the golden rule. An and is equal to the first thing precisely when the or is the second thing. Okay, and since I've already opened up some tabs, I can more clearly point to that example I was talking about. So here is this comparison I was talking about. So all the properties about and, this downwards arrow is minimum. Okay, so you don't need to know this for our class. I just wanted to. I thought it might help because the golden rule can appear strange otherwise. So there's a bunch of ways to read the golden rule, and here's one of them that I've written up for you. But I just wanted to show you that some of these rules are not that strange. Like idempotence, almost no one knows what that word means. And I just wanted to show you that it's like having no choice. The minimum of a number and that same number is, well, you only have one number. There's no choice to make a minimum from. Likewise, P and P equals P. So maybe let's prove that theorem. Let's prove P and P equals P. Unless somebody else wants to do something else. Okay. So, boop. So, theorem nice. Okay, so let's call this theorem nice. And this theorem is P, and P equivals P. So we'll start with P, and P equals something over here. And Control-Alt-Enter, and everything looks great. Okay. Oh, I forgot a word. Proof. Okay. So here's everything right there. Now the first thing to do is, I don't know what this and thing is, so I'll use its definition. Okay. And the only definition I have is the golden rule, which says this is P equivals to P equivals to P or P. Hey, wait a minute. Remember that thing called equivalence? We know a lot of properties about that. So let's call on the identity of that guy to get true equivals P or P. Okay, that looks great. But notice the identity of or, we can apply it again. All right, and we can simplify to just P or P. All right. So you can use a theorem multiple times as you're writing an expression. But wait a minute, we know or is idempotent. And so we just have like that. Okay, folks. So notice that every step there was essentially only one thing I could do. The goal is to simplify, right? I started with the complicated side, and my goal was just to simplify. And as I simplified, there was only one thing I could do to simplify. Identity of equivalence got rid of this thing. That was a simplification. I have a lot of stuff here. Idempotent simplified it to this one, right? So you know, if you're brute forcing your proofs, just be like, how do I simplify? How do I simplify? That will get you far. Sometimes it will not work though, and that's the theory of automatic theorem proving, right? Sometimes these things don't always work. Okay, ducks. So let's move on. And if you want more examples, or you want me to do another one, please let me know. Okay. So let's talk about the natural numbers. If you've used a for loop, then you've used natural numbers before. If you've counted, you've used the natural numbers before. So we're assuming there are no other numbers. We're starting with nothing. This is natural numbers from first principles. There's nothing else. Okay. When you enter a building and you decide to go one floor up, what floor are you already on? You're on the 0th floor, and you go one floor up to go to floor 1. So we're counting with 0 at the very beginning, and then to go to the next number, you put the word suck for successor. Okay. If you like, another way to think about it is an empty stack. So right here, look at this. This is empty. There's nothing here. It's empty. The empty piece of paper, right? The empty stack is 0. And then if you put, one book, this is a book, then you have the number 1. And if you put another book on top, that's the number 2. And if you put a third book on top, that's the number 3. And if you put the another book on top, that's the number 4. Okay? So you can think of suck to mean put a book on the shelf or on the floor. Right? So the empty floor is 0. Every time you put a book, then you've made a stack, and that's your number. Okay? So this is how we're going to think of numbers, as stacks of books, if you like, right? Or pancakes, or whatever you prefer. And we'll refer to the stacking operation as the successor operation. All right? So with this idea of stacking, then here's the idea. If I have a stack of books, right? So if n is a stack of books, and I put one more book on the stack, then I have a new stack of books. Okay, that sounds reasonable. The empty stack of books is a stack of books. Great. And nothing else is going to be a stack of books. These are the only things. To be a stack of books means You're either the empty stack, or you were obtained by adding a bunch of books onto the empty stack. Okay? So this is like proving a theorem. When you prove a theorem, you start with a known axiom, like the empty stack is a stack of books, and then there are some rules that you can apply. Okay? Now notice, two stacks are the same height precisely when they have the same number of books that I put on top of them. So this stack right here has 3 books, and this stack has 4 books. So if I start removing books off of my stacks, if they're not both empty at the very end, then they must be different stacks. So you don't need to count or anything. Just I give you 2 stacks and I say, are these the same height? And you just take 1 book at a time from each of them. And at the end, one of them will be empty. If the other one isn't empty, then they must be different. Okay? So this is called an inductive definition, or a definition by recursion, or a recursive definition, or an algebraic data type, or a union type, or an initial algebra. Has a lot of fancy names. They're very useful in programming and in mathematics. For example, the natural numbers are everywhere in math and in programming as loops, for loops. Okay, so see, this class is useful. We're talking about stuff for loops. And recursion. Recursion is great. Now, to prove a property, well, if you have a stack and you want to say this property is true for my stack, well, one way to show that the property is true for all of your stacks of books is to say, hey, for the empty stack, this property is true. When I have no books, I can check the property, and that property is true. Okay. If the property is true for a stack of books, right, then I can put one more book on top and the property will stay true. It won't change. Then I know that for any stack you have, you just keep adding an extra one to it, and the second rule will let me show that it's true. Okay. So just as this rule says, if something is a natural number, then putting a stack keeps it as a putting one more book keeps it as a stack of books. So what we're saying here is, if the empty stack has a property P, and adding books preserves P-ness, right? You know, like the property of having P being P-ish, right? Having this property. So every time you put a book, the property stays true. Then if you have a book stack of 23 books, well, you know the empty one is going to be true. It's going to have that property. And you know that putting books preserves the property. So you can keep putting books till you get to 23. Okay? So this is called the induction rule. It's also how loops work, right? If I want to say, hey, when you run this loop 0 times, the property is going to be true. And if the property is true, and then I run the loop 1 more time, the property will remain true. We'll clarify this tight relationship later on, but I just wanted to mention that. Finally, you can think of this as dominoes. Instead of a stack of books, if you arrange the numbers as dominoes, and you say, hey, I want to hit the 23rd domino. Well, first you have to be able to hit the first domino. You hit 0, the very first domino, and then you need to know that if I hit a domino anywhere in the sequence, if I was able to hit it, then the one after it should also be hit. So I want to hit the 23rd domino. I hit the very first one, and then they all fall. And then at any one point, the dominoes can't be so far away that they have to hit each other so that they all fall. Okay? So it's a cascading process. In case some of you don't know what dominoes are, I feel like I should show you what a domino is. 2 dominoes. There's one. Okay. So look, right? If you notice, they hit the domino right here at the very beginning on the left side. They hit it, and then the distance between any 2 dominoes has to be close enough that they hit over the remaining dominoes. Right? So the base case is you have to be able to hit the domino. That's the base case. And the inductive case is any domino must reach the next domino. Okay, so I just wanted to mention that as an example. And since we're online, I had a quick visual. So that's nice. Let's go back. All right. So that's all the induction principle says. And then later, when we get to order theory, you'll realize the induction principle says even something simpler than this domino idea. It says, if you remember, true is up here and false is down here. It says if P of 0 is true, we're already up here, and this P operation is increasing. Sorry, it's ascending. It's always going to go up. It's never going to go down. While I'm already up here, and this operation can only go up, it can never go down, then P of M is always equal to true. It's a constant function, right? So it says, if you have a function that starts at the top, and the function never goes down, then that function must stay at the top all the time. All right. So when you think about induction this way, it sounds useless. All right. But it's not a strange new thing if you think about it from these alternate perspectives. If I want all the dominoes to fall, I have to hit the first one, and I need to make sure the dominoes are not too far away. If I have a non-decreasing function that's already at the top, then it's going to always be constantly at the top. Okay. So if I want to prove a property for the numbers, I prove it for 0, and I show that adding suck preserves the property. All right. So there's not too much there. Okay. And as I mentioned, the idea of inference rules, if you have the stuff on top of the fraction bar, then you get the stuff below the fraction bar. Okay. And this is like addition in elementary school when you say 2 plus 3 and then a fraction bar equals 5. All right. So this is covered in chapter 2 and also extensively covered in the supplemental lecture notes if you're interested more about these inference rule ideas. And of course, inference rules to some degree correspond to axioms or theorems. Okay. Okay. So informally, we write these parentheses everywhere. But in the logic of this textbook, we use textual substitution, right? So to prove any Boolean expression P is true for all variables M of the natural number type, we first consider P with M replaced by 0, and we say, hey, if we have access to P, then we can show P with M replaced by successor of M. Okay. And again, this is like loops, right? If I want to show that this property P is going to happen, right, for this loop, I need to show that if the loop never runs, then this is going to happen. And between any two iterations of the loop, that P is also going to be true. Okay. And we'll get to this more later in the class as well. Okay. Now, in the standard way to write induction proofs is to say I have a theorem, and I'm going to prove my theorem by induction on a variable. Okay. When there's only one natural number variable, you do induction on that variable. Okay. Sometimes there's more than one, and this is where doing homework and exercises really comes in. If you pick the wrong one, life can be very, very hard, and you might not be able to prove anything. So there are heuristics about which variable you should do induction on, and we'll get to those in a moment, or maybe next lecture. And then the first proof, all right, the base case, you mark it explicitly. So a lot of textbooks will say, hey, here's the base case proof. So it's true for the base case. Now let me show the inductive step, and you get to assume that it's true for M, and you show it's true for suck M. Okay. So this is what a lot of books will do, and that's the approach we're following as well. But of course, we're doing it in CalcCheck. So let me show you just what that looks like in a moment. I have a proof somewhere right there. Okay. So it's just going to be just as you normally do things, right? Here's your theorem statement. You write your normal proof, keyword. Then you say it's by induction. And notice the backticks. There's a backtick here and a backtick there. Okay. Then you write the base case, what you're trying to prove, and then you write the induction step. Okay. So in this theorem, we're just proving M plus 0 equals M, right? Not sufficiently difficult. And notice you have two subproofs, right? There's one here, and there's one here. There's two proofs, okay? And if you as I said in the style, right here, you can write down your explicit goal. You're proving that P of 0 is the point of the base case. That's what you're trying to show right there. And you can write that down using the syntax as well. So here's the original one. As always, we're always indenting by 2 spaces. So we always want 2 spaces indentation. Okay. So here's just to remind you. And if you look on the calc check manual, there's a way to toggle displaying these space markers. In case you have trouble and you want to see the space markers, there's a way to toggle them on if you look at the calc check reference manual. Okay. And notice the subtle distinction. Here, I just said base case, right? Just base case. But maybe you want to remind yourself, what is it you're actually proving? You're proving this thing with M being 0. So maybe you want to write that down. You want to document it for yourself. And so you can do that by using backticks. Okay. If you have a backtick, you can write down what it is you're proving and what it is you're proving there. At the very beginning, I highly recommend you all put backticks and write down explicitly what you're proving. Because when you put the backtick and say, I'm proving this, calc check will actually check, is that what you should be proving or not? So if you think I'm proving this, but calc check thinks you're proving that, you want to be notified. Otherwise, you'll get all these strange errors and you think you're doing the right thing, but calc check says, no, you're not. So it's very helpful to document, to communicate what you're doing to calc check so that it knows what you think you're saying. When you're learning stuff, you might think things are a way, but they're really a different other way. So it really helps to communicate how you think of things. And then the machine will be like, yeah, you are thinking the right way. Or I'll be like, no, you misunderstood. All right. So a helpful thing to have. Since we have a bit of time, I'll go over this other slide I skipped really quickly. I was just worried about time. So induction lets you prove things, but it also lets you define things, right? Remember when we talked about defining textual substitution? We said to define textual substitution, well, this is how it behaves on variables. And when there's a function application, you throw textual substitution inside, right? So we defined it on the possible shapes. When we talked about defining program correctness, we said to define the square bracket implication arrow, you look at the shape of the program. If it's an assignment, you use the assignment rule. If it's a sequence, you use the sequence rule. Okay. So likewise, when you define operations on inductive data types like the natural numbers, you look at their shape, and then that's how you define it. So for example, suppose there's n people standing in a line. And you have n people and you want them to stand in a line, right? How many possible lines can be formed from n people, right? Well, if there's 0 people, right, then there's only one line, the empty line, right? If you have n plus 1 many people, then how many lines do you have? So the factorial operation, right, can be how many ways to arrange n objects, right? So how do I arrange n plus 1 objects? Well, first, I pick one of the objects to be at the very front, and then I consider all the ways to arrange n minus the remaining objects, right? So I can define the factorial operation using these 2 clauses, okay? And when you define things using induction, you prove them. When you define things inductively, you use induction to prove properties about them, okay? So here's another example. So you saw even on the midterm, right? And you can define even by saying, hey, 0 is always even. Notice there's no equals true, remember? Right? So even 0 equivales true, right? Something you just put in your head. So even 0 is true. And then if the shape of the number is not 0, but in fact is the successor of some other number, then I say, oh, in that case, the number n plus 1 is even precisely when the number before it was not even, because the numbers they toggle. 0 is even, 1 is not, 2 is, 3 is not, 4 is, so they just toggle. Right? Yes, no, yes, no, yes, no. Right? So we can define it this way, right? And we defined it on the 0 case, and we defined it on the on n plus 1 case. And even though in this definition we call even itself But notice we call it on a smaller thing. And so that's okay. That means if I invoke, if I say even of suck 5, like 25 sucks, the second rule will give me a bunch of knots, and then eventually I'll have even 0. Okay, so because the call to even on the right hand side is on a smaller argument, structurally smaller, this is okay. All right. So we'll get to this notion of being well defined later on as well. Okay. I would like to do some proofs, but unfortunately, it seems I'm out of time. So thank you for coming to lecture, and all the best. There is a homework, so that will get you ready for inductive definitions. So next midterm, we'll have inductive definitions, and it will have and it will have or. But it might, of course, it will also have equivalence and negation. So just building up. And hopefully we'll get to even more and more fun stuff. So yeah, thank you again, and have a fantastic weekend. Goodbye. Right.